I'm Bruce Bugbee, president of Apogee Instruments and professor of crop physiology at Utah State University. So today I want to talk about our latest spectroradiometer, the features it gives you for plant photobiology, and on the screen itself of the instrument. We have other videos that are like owner's manuals of this. I'm going to focus on interpreting the data from this. This instrument has got a tiny screen right here. So you make a measurement like this, and instantaneously, or within seconds, it gives you the calculated values in here. And that's what I'm going to go through. There are 5 screens in this, and I'm going to go through each of them and what the values represent. Here's the instrument big. It's a model MS100. Minutes ago, I walked outside and took a measurement in sunlight. That sunlight's a wonderful reference spectra. So it's close to solar noon here in Logan, Utah. So let's take a look at what these values look like with sunlight. There's a sunlight spectra, and this shows up immediately in the screen. If this was an LED, we'd get a spike of blue and fluorescence. It's an immediate spectral trace of the light you're looking at, which is really helpful. Immediately you can interpret a lot of stuff just from this screen. No downloading of data, just click the shutter speed in the instrument and collect this. There's a lot we can do with this screen, and let me put some units on this right away if you're less familiar with this. First of all, this tells you something. Let's get a color in here. Let's put this in green. We've got 1, 2, 3, 4 tick marks in here. If you're familiar with the sunlight spectra, this is UV, this part right here. So this instrument detects down to 350 nanometers, which is most of the photons, by the majority of the photons even from sunlight. And then the first tick mark is 400 nanometers, then 500, 600, 700, and then out here is 750. So the subsequent screens tell us the number of photons in each of these categories. But first of all, 4 to 500 is B for blue photons. 5 to 6 is G for green photons. 6 to 7 is red for red photons. And then this critically important part out here, 700 to 750, is FR, far red. So UV, put that on here, 1, 2, 3, 4, 5 categories of radiation. Now it downloads the spectra, so you can fine-tune this as much as you want. But for quick analyses, the fractions of photons in each of these categories are particularly important. This axis is, of course, photon flux. That's an F. And it's micromoles of photons per meter squared of area per second. And now, because this is all these little tiny bins, it's per second per nanometer, as the spectroradiometer gives you. When you download the spectra to a laptop or to a cell phone, it gives you more data than this. This is just the screen it shows. That's the opening screen. Make sure you got the correct spectra in there. Save the spectra. Now let's go to this. So this is screen number 1. Now let's go to screen number 2. And we're starting to parse out these ratios. PPFD, as we've talked about in previous videos, PFD is the photon flux density, and P is the photosynthetic photon flux density. And this means 400 to 700 nanometers. And this is the classic definition of photon flux density that we've used for over 50 years. Sunlight, we always say, goes up to 2,000 micromoles. The units over here for these are all micromoles per meter squared per second. So this serves with this metric as a regular quantum sensor, a high resolution quantum sensor, and we always say sunlight goes to 2,000. Well, right now in Utah it was 1,948. Maybe there was slightly overcast, or it's not exactly solar noon, but it's close to 2,000. Now, E, this lowercase e, stands for extended photosynthetic photon flux density. And what this means is 400 to 750, that's a 7, nanometers. Same units here, but it adds the far red photons to this that, based on lots of research, have photosynthetic value. So it gives us both numbers. Now look, 1923, this is adding some far red photons in. The difference would be the far red photons here. Those are actually shown on another screen, but this ought to be slightly higher. If you measure this under red and blue LEDs, there's virtually no far red. These numbers would be almost the same. But if you measure under white LEDs, they have a tail. So the ePPFD is almost always a little bit higher, and sometimes much higher if you're measuring lights that have a lot of far red photons in them. So these are pretty straightforward. We've covered these in previous videos. I won't write out the full acronym right here. But now there's a third metric in here. Y, PFD, photon flux density, the same as these. The Y stands for yield. And this is a metric we've had for 50 years, and it does not weight all the photons equally. These do. A blue photon counts just as much as a green and a red. They're all equal. That's our definition of these. But we know that particularly blue and green photons aren't absorbed as well by photosynthetic pigments as red photons. So this metric weights the photons, weights the red photons more than the blue and more than the green. And because of that, this is always a number slightly smaller than this. Many researchers report all of these in their papers to make sure you've got all the metrics. In theory, YPFD is a more accurate predictor of photosynthetic photons than PPFD. And we don't have it yet, but in theory you can have an EYPPFD. I'm making that up just now because that doesn't exist yet. But this is this weighted, so I'm going to cross that out. This is a weighted flux of photons, and it's always about 90% of these because it discounts blue photons for photosynthesis. Finally, to round it out, T stands for total photon flux density. See how this number's higher? This is everything the instrument measures, and it's 380 to 780 nanometers. This is all the photons. At the edges of this, it counts the UV photons in this, counts all the far red photons, and it's a bigger number. Each of these metrics is valuable in photobiology depending on the study, depending what you used. But the beauty of this is you click the shutter, you take a measurement, and you have these numbers immediately right there. They're stored in memory, but you have them right there to analyze. This is screen 2. We have 5 screens. Screen 3 puts these photon fluxes in categories. Remember, UV is 380 to 400. So there's the flux. There's only 38, round this number to 39 All of these units are micromoles, again, per meter squared per second. So this is sunlight, 39 micromoles of UV photons. B is for blue, 400 to 500. 500 for blue, and you can see in sunlight it's a little more green and even a little more red. That curve goes up. Here's the green photons, here's the red. Now, if we sum these up, we would get the total photon flux. If we just added these together, we would get the ppfd, but this breaks it down into categories of photons. This is screen 3. And depending on what you're doing, this is really useful to be able to immediately see the number of photons in each of these categories. Screen 4. This focuses on far red photons. They are such powerful photons. There's 4 critical metrics for far red photons. And remember, the far red is, where am I going to put that? Is 700 to 750 nanometers. This edge, we can barely see it, but it's very, very powerful for plant growth. This is the photon flux of far red. Now this could be on the previous screen, but there's 4 numbers on each screen. So there was 357.5 far red photons in sunlight right now when we made this measurement. FRF stands for far red fraction. So this is far red photons over total photons, ppfd. And in this case, it's E, ppfd. So you can see this is a number that goes from 0 to 1, the fraction. If it was pure far red light, the numerator and denominator would be the same, it'd be 1. This is a very convenient. We look for ratios that are 0 to 1 in all of our science. So because it's a fraction, it's 0.15. If this was a percent, we'd have 15.5%. And that's pretty close to the typical far red fraction in sunlight. It's a real useful number because we get so intuitive. Was there 5% far red photons? Was there 20% far red photons? We've used this in manuscripts. Paul Kasum and I have a manuscript on the importance of far red fraction. It's becoming very widely used in photobiology to describe the amount of far red. PPE is a different metric. I can leave this other one up here. This one is for phytochrome. Phytochrome photoequilibria. It's also called, I'll put this here, let's see, let's switch to yellow. This is also known as PSS. They're exactly the same thing. This stands for phytochrome photostationary state, phytochrome photoequilibria. Same number. This is a number that also goes from 0 to 1 depending on the amount of far red light. And I'm going to show you a few slides to explain that in a minute. This was 0.69, which means there's quite a bit of far red photons in sunlight. But this weights all the photons over the entire spectrum for whether they contribute to stem elongation or not. And stem elongation is largely controlled by phytochrome. So we have a final metric on this screen, IPPE, and I stands for internal. What this means is the predicted phytochrome effects inside the leaf. not above the leaf, but inside the leaf, internal to the leaf. This is a new metric, IPPE, and our data indicate it more accurately predicts stem elongation under a range of colors of light than the old metric, which was PPE. Now we show both metrics, you can compare, and my colleagues have been putting both metrics in their papers to predict things like leaf expansion and stem elongation, but this predicts both. Now look, this is 69 and this one's only 39, so there's a big difference in these two metrics. And what I'd like to do is take a little sidebar right now and show you some slides that I showed a few weeks ago at a big NASA conference to explain the significance of these metrics for plant biology. So let's go to those slides, and we'll come back to this one right at the end. This is improved metrics for photobiology. These are just slides from that talk. This is a picture of the phytochrome molecule. It's a big organic molecule with a lot of proteins in it, but it switches back and forth between two forms depending on the colors of light, mostly red and far red. So it's great to think of this as nature's light switch, because it's either on or off, telling the plants you're in the shade, get tall, you're in the sun, stay short. But it just switches back and forth between these two, and you need a spectroradiometer to calculate which form it's in. And that's interesting because there's thousands of these molecules in plants, and the plant is integrating all of these light switches to decide whether it should get tall or whether it should stay short. Here's sunlight. This is the significance of this simply. In shade, plants have a choice. They can avoid shade and get tall, or they can tolerate shade and grow more leaf area. Now here's a plant in sunlight over here. It's short with small leaves. What we can do with photobiology and lights is trick these plants into thinking they're in the shade so they get more leaves. And that's a wonderful thing. We trick them to think they're in the shade. Some species get tall, and this is very undesirable. But this is that curve we were just looking at for sunlight, measured under the sun. Here's our classic 300 to 400, 500, 600, 700. Now look what happens in the shade. Underneath the tree, all of these wavelengths are filtered out, and this far red, we better put that in a darker color. This far red right here is transmitted, and it flips that phytochrome molecule to the on position, and it says, change shape, we're in the shade. Even whether they're in the shade or not, we could trick them, but in nature, this is how it works. There's the far red, the critical in shade. This is the classic ratio of colors that leads to this metric, phytochrome photoequilibria, and it's a ratio of far red. Let's get another. It's really a ratio of far red over total photons, and it heavily weights blue photons and less of red. So we've known about this curve for 60, 70 years. In studies, I picked one here from 1976. This is this PPE. As the number gets higher, stems get shorter. And actually, this is not quite correct. PFR responds to the red photons, not the far red. So as this number gets higher, more red light, plants get shorter. And that's a pretty good predictor of this. So you measure it and you know the potential of your light source to make tall plants or to make leaves expand. Okay, this was worked great. But the phytochrome molecule is not just on the surface of leaves. It's inside the leaves. And here's these blue photons. We keep coming back to these same wavelengths here. Blue photons are absorbed by chlorophyll and other pigments, and they don't penetrate the leaf. This is a cross-section of a leaf, top and bottom, blown up. Green photons penetrate into the leaf, and this is the transmission here. Red photons don't. They're absorbed. Far red really penetrate into the leaf. So what does the phytochrome molecule actually see? It sees the penetrating photons into the leaf. So when we did tests on the old, this is the old PPE right here. This wonderfully predicts, this is a nice linear relationship, stem elongation. When we did that test with different ratios of colors in the background, blue, green, and red, the lines got all mixed up. The predictive value of PPE was not very good. So we have a problem with the PPE under LED lights where there's a mixture of colors. So let's look at what we did. Here's the old curve. This, by the way, is done with Paul Kasuma, a PhD student with me. He's now an assistant professor at Wageningen University in the Netherlands. This is the paper this came from. Here's the original PPE right here. Put that in yellow. With the weighting factors that we've used. Here's the screening of chlorophyll, the classic screening. More green gets through, a lot more far red. If we take this times this, we get this function. And this function is IPPE, which your new spectroradiometer measures, calculates instantaneously. And look at the difference. This heavily weights red, this heavily weights far red. How well does this newer metric predict stem elongation under a range of light sources? Very well. Here's I. This is the PPE. Once again, same curve I've been showing you. This is PPE with colors, and this is IPPE, the new metric with a big background of colors, and the lines converge. So this, coupled with other people's studies now, indicates internal PPE is just an improved metric, more precise for measuring phytochrome effects, considering what's called the spectral distortion of the leaf, the filtering of chlorophyll into the leaf. That's a lot of slides to derive why IPPE is important. Let's go back to the spectroradiometer. Here's PPE and IPPE one last time. We show them both, the older metric and the newer metric. And this is more sensitive to, on a range of 0 to 1, this is more sensitive. These numbers tend to be all very high, 0.7 to 0.9, whereas these numbers are 0.3 to 0.9. This is screen 4. We have one final screen. This is screen 5, and these are metrics for human lighting. Color rendering index, which most people are aware of, it's a number of 0 to 100. The closer to 100, the better the light source renders colors for the human eye, the reds and the greens and the blues. Now, 0 to 100, this is sunlight, and that's the reference. So the color rendering index then when it's which is an index, it usually means a number to 0 to 1 or 0 to 100. Sunlight's a reference. What's CFI? This is the color fidelity index. This has been called by some people TM30 for technical memo 30. It's also called RG. But it's an index 0 to 100, so we call it the color fidelity index. And look, under sunlight, 100. It's as good as it gets for color rendering index. This is very close. Under LEDs, this number gives bizarre values. It gives negative values. It's an old index. The CFI is a much improved, newer index, and people say, oh, the calculations are more complex for CFI. For one, this is based on 6 reference colors. This is based on 99 reference colors. That tells you something about how superior it is. And people say, oh, the calculations are so complex. Oh, yes, well, it takes about 5 microseconds to do those calculations in a computer. So this CFI is replacing CRI. And in fact, I would say it's largely replaced it, but this has been around a long time. Finally, and let's see if we can erase these. Give ourselves a little bit more room right here. And we'll put this in yellow. Color correlated temperature is a number between about 2,000 and about 7,000, depending on really the blueness versus the orangeness of the light. Now, the higher the number, the more blue the light. And this is sunlight, so it's 5,000. So sunlight's very blue light. If this was an incandescent light, this number might be about 2,000. And you go to the store and you buy LEDs, and you can pick whether you want to simulate an old incandescent light. Incandescent light's about 2,500. It's a warm, orangish glow. We say you put warm colors in your bathroom to make it look like you have a good tan, and cool colors in the kitchen to be more like sunlight in the kitchen. So this gives a number from 2 to 8,000, depending on the blueness of the light. And finally, the old classic, lux, which is the weighted human eye response for lumens of light. Lux, the definition is a lumen per meter squared is a lux. Sunlight's about 10,000. Foot candles, by the way, FC, we used to use those, is a lumen per foot squared. But this is the metric equivalent of foot candles. And we put this in here just because it tells the brightness of a light for the human eye. It has nothing directly to do with plants. These, turns out, have quite a bit to do with plants because we want to accurately diagnose subtle differences in color of plants. And the higher this color fidelity index, the better we can see the plants. So, there you have it. 5 screens. First one is a graph. Screens 2, 3, 4, and 5 are summary metrics of the light. We hope you love this instrument. We've been using it in my laboratory at the university, the graduate students and I, and this is the go-to instrument because it's so fast and easy to use, and it gives you these ratios right on the instrument itself. Thanks for listening.